Okay, so let's touch on the efficiency of Turing machines and the theory of NP completeness. Now, of course, if you want to get more details, read chapters 28 and 29. Okay. Now, to focus the discussion, let's consider a very simple problem. So, the language, which is a problem, computing problem, is 0 to the n pound 1 to the n. So this is the equality problem. Okay, and let's build a Turing machine to solve this problem. A very simple Turing machine, and I'll illustrate it on tape, okay, on an example. So we have a very simple example. Okay, imagine that we have 0, 0, 0, 0, pound 1, 1, 1, 1. For good measure, we have a blank symbol here. Okay, and as usual, we have our beacon. Okay, so our Turing machine starts here. Now, how would we solve this problem? And with a Turing machine, it's actually relatively easy to solve this problem. You come and mark this 0, then match a 1, then come back and mark another 0, then match a 1, then come back and mark another 0, then match a 1, mark another 0, match a 1, and then there are no more zeros to mark, and there are no more 1s in here, and so you're done. Okay. So if we look at how this Turing machine moves, you see that it's going to move to here, it's going to move here, and then it's going to move here, then it's going to come back, then it's going to move back. Then it's going to come back, then it's going to move back, then it's going to come back, then it's going to move back, and so on. So it moves back and forth. So if we call this number of bits n, the total number of bits, well, it's approximately, twice the number of zeros. So the number of zeros is approximately equal to n over 2. And so it's going to have to make a zigzag like this for each 0. So it's going to make n over 2 zigzags. Okay. And each zigzag travels approximately n over 2 and n over 2 back. So each of these corresponds. So each time the machine has to move, that's a step. And we can imagine it takes a unit of time to make one step. So each zigzag involves n moves. So a total of n times n over 2 moves by the Turing machine head. So theta of n squared moves, which roughly speaking is the running time. Let's call this machine M1. Okay, so M1 has a running time in theta of n squared. And we're familiar with asymptotic notation. In fact, that's one of the reasons we introduced asymptotic notation, to analyze running time of algorithms, and algorithms are Turing machines. Okay, now, challenge. It's possible to construct a Turing machine which improves on this, whose running time is n log n. Theta of n log n. So you can, take up this challenge and try to figure out a Turing machine, specifically, an algorithm that would, that has only the basic capabilities of the Turing machine and that runs in n log n. I leave that as a challenge. You can read chapter 28. It has the details of how you could do this. I want to focus on something else. Okay. Supposing now that, I add a twist to my Turing machine. I add some parallelism. I make the architecture parallel. So I give you 2 tapes and 2 tape heads. Okay, so you can imagine that there's a master tape, okay, with 0, 0, 0, 0, pound 1, 1, 1, 1, and for good measure we have the blank symbol to show you that we end the input there. Okay, and you have your usual beacon symbol. Okay, and you have your head for your master head and your first tape, and I give you a second tape. So this is a more sophisticated, more elaborate Turing machine. Okay, it's got more than one tape, in particular 2 tapes. It could have more, could have 10 tapes, 50 tapes. I'm just illustrating with 2 tapes. Okay, blank. These are all blank. Okay, so these are all blank. The input is on your master tape, let us say. And you've got a second head that can move along this tape and a head that can move along that tape. And your Turing machine CPU, your DFA, can control each of these heads independently. Can we solve the problem more quickly? And the answer is yes. And here's the basic algorithm. Take this head and move it right. So at each step you move it, you read 0, and simultaneously move this guy right. Whenever you read a 0, write the 0 here. So you move this guy right. Okay, and every step you move, you read, and then you move this guy right and copy that symbol to here. So essentially you can think of this as I'm copying. So I have 0, 0. I'll end up writing 4 zeros. Okay, so now this guy's head is over here, and this guy's head is over here. This guy's head is over here after the copy. Okay, great. Now, I continue moving this guy right, and for every one, while I'm moving this guy right, I move this guy left, and for every one, I check that there's a corresponding zero. If I come to star before I end the ones, there were fewer zeros. If I end the ones before coming to star, there are fewer ones. And if when I end the ones I'm at star, okay, there are exactly the same number of zeros here, which is equal to the number of zeros here, which is equal to the number of ones. So I just go back now. I continue here, and I go back, checking off each one with a zero. Okay, so let's see the number of moves that are made. This guy scans half, then scans half. This guy goes forward and back. So this is n plus n is 2n. Okay, so in theta of 2n steps, which is theta of n, in asymptotic notation, we get rid of these baby constants. I can solve the problem using M2 tape. So M2 tape. You can think of this as a parallel architecture. So parallel architecture, adding multi-threading, adding parallel capability has significantly improved the running time. Okay. Interesting. So maybe I should go to 3 tapes or 4 tapes. Well, it turns out, and you can see the proof of this in chapter 28, it turns out that, 2 tapes, 3 tapes, 4 tapes don't add significantly more capability. Okay. Now, the point that and we'll get to that point, okay, but the real message here is to look at these running times and notice that they're all polynomial. They're all polynomial. And why am I pointing that out? Okay. Because what I'm essentially saying is that the running time was polynomial on a single tape. Now we can try to improve it, but it's still polynomial. The running time is polynomial on the 2-tape machine, and we can try to improve it. Maybe we can get n over 2, but it'll still stay polynomial. Could we get log n running time with some number of tapes? The answer is no. So you cannot get exponential speed up from going to multiple tapes. You can only get a polynomial speed up. For example, n squared to n. Okay. So theorem. You cannot get exponential speed up from going to multiple tapes. You cannot. In fact, the theorem is a little bit more elaborate. So the theorem says the following. Let's say you have a multiple tape architecture with some fixed number of tapes. Let's say k, for example, 2. Okay. And in your multi-tape architecture, let's say the running time is t of n. Okay. Then we might ask, what's the best you can get on a single tape? Single tape, okay, we can show. Okay, and this is called the simulation theorem. So single tapes can simulate multiple tapes with at most a squaring slowdown. So if the running time is t of n on multi-tape, then the single tape will have a running time at most O of t of n squared. That's very interesting. Okay, so let me sort of break down what I'm telling you. What I'm telling you is that if you can solve a problem in a parallel architecture, so parallelism, okay, you solve a problem in a parallel architecture like this, 2 tapes, okay, you can solve that same problem on a single tape architecture, so no parallelism, and the running time will at most square. So you might think, oh, but squaring is a big deal. Yes. So for example, if this is n cubed, this becomes n to the power 6. Okay, and that's the worst case. Worst case is it can become n to the power 6. Okay, and then you say, yes, in practice we do care, and yes, in practice we do care about the parallel architectures. That's the kind of speed ups they can give you. But okay, in theory, something interesting is popping up, and let me sort of try to convince you that this interesting thing is very interesting. So what it says, okay, is that if your running time on some architecture is t of n, then your running time on the single tape is t of n squared. Okay, let me rephrase that in a way that's going to be more useful. If it's polynomial, if your running time is polynomial in some architecture, then it's polynomial on the single tape. Why? Because it's going to be polynomial squared. And the square of a polynomial is polynomial. Okay, and so this is one of the things that justifies the notion of polynomial as a sought-after property of an algorithm. Okay. We like our algorithms to be polynomial, and we don't distinguish between n and n squared, not because in practice n and n squared are different, but because polynomial is polynomial on any architecture. Okay. So this sort of leads us to define this robust notion of speed. So we say that a problem can be solved quickly if it can be solved in polynomial time. And that motivates the definition of the class P, the class of problems that can be solved in polynomial time. So the class P, the class of problems that can be solved in polynomial time. Okay, and then you would say, but wait a minute, in polynomial time on what architecture? Okay, and that's where this discussion comes in. Doesn't matter. Single tape, parallel. If it's polynomial here, it's polynomial here. If it's polynomial here, it's polynomial here. And that is the extended Church-Turing thesis. It says that, all reasonable definitions of Turing machine, parallel architecture, single tape, can your Turing machine stay in the same place or it must always move? Okay, all various reasonable definitions of Turing machine, they preserve this notion of polynomial. So a polynomial on any Turing machine is essentially a polynomial on the standard single tape Turing machine. Okay, so architecture independent. This means that we have a notion of fast that is architecture independent. And that is why polynomial has stood the test of time. Okay. In order to, if something is not polynomial on my architecture, in order to break that, you can't do it by just going to parallel. Okay. You need something fundamentally new. Okay. So polynomial is architecture independent. Okay. So let me give you an example, some examples of problems that can be solved in polynomial time. And now we don't need to specify the architecture. That's the beauty of this equivalence between various types of architectures and the single tape. If it's polynomial on any architecture, it's polynomial on all architectures. Okay, so let me give you some examples. Okay, network flow. Okay, what's the fastest rate at which I can send packets from here to Washington, D.C.? Network flow. We can solve this in polynomial time. So it's efficient. There are fast Turing machines like these guys, polynomial time that solve, network flow. Making change. Make change. So in the US, we've got, the penny, the nickel, the dime, and the quarter. And I might ask, well, I want to make $1.27, 127 cents. What's the fewest coins I need, to make that change? We can solve that in polynomial time. Can solve it very efficiently. Finding the optimal highway system that uses the least amount of material to build roads, but connects all the nodes in a road network. That's minimum spanning tree. So minimum spanning tree. Efficient. Euler path. So how do I plow all the roads while visiting every road once? Efficient. Euler path. Sorting. I give you a list. Can you tell me, is it sorted or not? We can solve this problem efficiently. It's all polynomial. Lots of problems that we like to solve in practice, and we can solve them fast in polynomial time. So that is the class of problems that we call P, the class of problems that can be solved in polynomial time. Well, are there problems that we cannot solve fast? Okay. So remember, now we're only talking about solvable problems, problems that can be solved by a Turing machine decider. Okay. So are there problems that we know cannot be solved fast? Yes, we call those problems exponential problems, or EXP. Okay. Cannot solve in polynomial time. Just cannot. Okay. We can prove it. Okay. What are examples of this? So most complex games that involve multiple complex strategies and, multiple ways, in many ways in which the game can flow, so exponentially many such ways, are provably non-polynomial. For example, chess. What would it mean to solve chess? So to solve chess, it means I give you a board position and I say, who wins, black or white? So you say yes if it's black, you say no if it's white. Okay. So such games typically cannot be solved in polynomial time. So they are in exponential. They're in the class of problems which we call exponential or EXP. Not ESP, EXP. You can't solve them with ESP. You can solve them with algorithms, but those algorithms take a long time. Okay. Exponential time. Okay, so there's a boundary. Okay, we can call this boundary, let's put this boundary here. Okay. And every problem is either solvable in polynomial time or not solvable in polynomial time, in which case it requires exponential time. Okay. But now here is the problem. In theory, every problem either belongs above the line or below the line. In practice, and also in theory, there are many important problems for which we don't know which side of the line they belong. So this boundary isn't a thin line, it's a very fuzzy, thick region. So this boundary is a fuzzy, thick region. And what do we mean by that? Okay, so that's what we're going to discuss.